guys, welcome to our discussion. Today we're going to look at a concept in stoichiometry of chemical equations, and that is the concept of ionic equation. Ionic equations are derived from the stoichiometric equation that we talked about, and in this case we are going to see different kinds of ions, specifically the ones which are taking part in a chemical reaction and the ones which are maybe remaining dormant or idle. We are going to have specific names to refer to these kind of ions by maybe using some of the examples that we're going to illustrate on the board. So without further ado, thank you and welcome. So for today, we are going to discuss on the concept of ionic equations. The last time we discussed in some of our videos, we talked about the concept of stoichiometric equations, and we represented them using the symbols, the reacting volumes, and the states of those specific reacting species and the product. So for today, we are going to use also a few examples in order to illustrate what basically an ionic equation represents. And by definition, an ionic equation is an equation that represents a chemical change by means of ions instead of using the reacting species and the product or chemical symbols that we basically used in the stoichiometric equations. So we're going to do this using some of the examples. So basically this one uses, or maybe I can just write it in full. So this is an equation that will represent a chemical reaction by means of ions. So basically for these ions, from the general definition is that ions for the reacting species and the product, instead of symbols of compounds. So sorry for that. So this is just a rough definition of what I'm trying to imply, whereby instead of using the chemical symbols like the ones that we used in discussion of stoichiometric of chemical equations, like for instance the sodium chloride, this is a symbol of a compound. So this one in ionic equation is represented as sodium positive and chlorine negative. So therefore we're going to do an emphasis on that one instead of this one. So from that statement, this is just a summary of what it refers to. So I'm going to give an example so that we can be able to look at how we can represent that specific reaction in form of ions. Now suppose we have a reaction between barium chloride and sodium carbonate. We'll have an equation that is representing the reacting side or the reactants and the products given as such. But of course this equation for us has not been balanced, so therefore we are going to have to represent this equation in form of a stoichiometric equation by trying to look at this. So the bariums are 1, the chlorine are 2. So we're going to have 2 represented on that part of the product side, and basically this is going to be balanced as such. So we have a stoichiometric equation. Now from this stoichiometric equation we can be able to derive an ionic equation, which is going to represent the ions that are going to react in order to form products. So we're going to see that there are 3 possibilities during ionic changes, and this is going to give us a representation for that. So we can be able to give this kind of compounds in their individual ions which form the product. Like barium, we have barium and then it's combined with the chlorine. This is on the reactant side. So we also have sodium, which is combined with a carbonate, and then it's forming barium carbonate, which is a solid of course, plus sodium plus chlorine. So I've said that we have possibilities that are going to occur during an ionic equation, and we're going to see the 3 conditions of course for that. So I've not balanced this representation for ions, so I'm going to do that by trying to compare. So the barium chloride, we have two chloride ions in that reaction, and then for sodium as well we have two, and then for the carbonate it's one, and then on the other side we have two sodiums and two chlorine. So basically I'll write the states of these ions. Aqueous, and then this is a solid. So we're going to look at which ions have combined to form a product and which ones have remained just as what we refer later to as spectator ions, by trying to look at the product, I mean the reactant and the product side. Now in this case we are going to see that the chlorine ion are present on the reactant and the product side. So therefore we are going to consider these ones have not changed, not have changed. And the ones that will not have changed for this is the sodium ions. They are still remaining in their state, which is the same. So therefore we are going to have barium ions reacting with the carbonate ions to form barium carbonate. So if we do just a particular reaction or a specific reaction in the laboratory for this, we're going to have a solid that is going to form, which is of course a precipitate, and this precipitate will show the presence of a barium carbonate. Now in this case there is a specific term that we use to refer to this species of ions which have not taken place in the chemical reaction or in that Ionic equation. Now we refer to them as spectator or watch ions. Watch in a sense that they just stay put without taking part in the chemical reaction. Now the equation that we have come up with from this specific representation is what we call an Ionic equation. Now there are three possibilities which I said sorry for that. We're going to mention for formation of Ionic equations, and we're going to see that these possibilities include the formation of basically the three states of matter that we generally first in our basic introduction about the solid, liquids, and gases. So in this case, there's a formation of a solid, which is barium carbonate. So first there's a formation, the first possibility, formation of a precipitate, or we can just refer to it as a solid. And then there's a formation of a liquid, like water. Maybe we can have an equation whereby if we eliminate the spectator ions, we're going to have reacting ions forming this kind of a product, which is a liquid. So in this case, the statement number 2 refers to that particular condition. And the last one is a possibility of formation of a gas. And we're going to see by using an example of either of those specific equations that we've mentioned for the three possibilities. Now let's look at another way in which we can be able to represent Ionic equations. For instance, this is a reaction whereby we are having exchange of radicals for the barium and the chloride respectively. Now suppose we have maybe a reaction, another kind of reaction that is maybe a redox reaction. For instance, if we have a zinc reacting with a HCl gas, there's going to be formation of a chloride and production of hydrogen gas, which is going to be represented as this. So therefore we are going to see whether the equation is balanced. So this is 2 for hydrogen, zinc was okay, that is okay. Now this one we can as well break it into individual ions which are reacting by having zinc reacting with the those from acid to form zinc. It's an ionic compound, so therefore we're going to split it to have zinc plus the chlorine, the chloride ions plus hydrogen gas. So looking at this, we're going to see that whatever ions that have not been affected, as we said, we refer to them as spectator ions. These two species of ion for the reactant and the product have not been affected. So therefore, we're going to have a resultant equation, which is an ionic equation represented. So this is, we said that we have to write the state of this specific reacting species and the product. So therefore, we're going to have zinc plus 2H positive, forming zinc 2 positive plus hydrogen gas. So sorry for that, this is hydrogen gas. So we can see they are balanced, so this is a solid, aqueous, and a gas. So that's an ionic equation that can be represented using that specific. And we're going to use the same analogy in trying to represent other kinds of reactions. Maybe it's a redox reaction like this, displacement reaction, maybe it's an oxidation, or maybe a reduction reaction. For instance, this one is an oxidation reduction reaction whereby zinc is oxidized by this oxidizing agent and the hydrogen is reduced by this reducing agent respectively. So in this case, this is how we're going to represent the ionic equation by trying to write a stoichiometric equation and breaking it down into specific ions which are taking place, and then trying to see which are spectator ions and ions which are taking part in that chemical reaction. So I hope we have understood the concept of ionic equation, which of course basically is a derivative of the stoichiometric equation that we have discussed already in some of our videos. So this is a strategy that we're going to apply in order to write the ionic equations in any of the challenges that maybe require us to do the same. So that is it for today. Thank you. Bye. God bless.